Hello, I'm going to walk you through the basics of Michaelis-Menten Kinetics. This first video is going to focus on the foundations of what enzymes do, how they work, and some of the basic math. So, what happens is the body wants to turn substrate into product in the body. You will say you start out with CO2 in the muscle and you want to convert it to H2CO3. Which then can be converted back in the lungs to be excreted out. You want to get rid of the CO2 byproduct in the muscle. So you obviously need some H2O, but that's floating around in the body, nice and easy to get. So what actually happens is you have the substrate form a complex with the enzyme. This then can form the product plus the initial enzyme. The rate in which this goes to that we call KF, K the forward reaction. The rate in which this goes backwards to the initial bit we call KR, K of the reverse reaction. And then the rate in which the complex goes and forms what you want, the product, we call KCat. So, as you can imagine, it would be pretty hard to measure KF, KR, KCat. Off the top of the head, you might not be able to think of a single way you could do this. Well, it seems a lot easier just to measure the substrate concentration and the product concentration. And so that's what we actually do. And we convert these three terms into one new one that we call K sub m, the Michaelis-Menten constant, which is equal to KR plus KCat over KF. As you can see, this is the reverse reaction. So this is the reaction that goes from this to the beginning. This is the forward reaction, which goes from this to the product. This is the one that forms it. So if Km is big, that means that the enzyme doesn't like to be bound because it likes to go in the reverse reaction. It likes to go in the forward reaction, and doesn't really like. It likes to go in the product reaction, and doesn't really like to go in the reaction that actually forms the ES complex. So you keep on saying enzyme substrate complex, and you're like, okay, I have no idea what that means. So what's basically happening is you have the enzyme, big protein, the binding pocket, which then has CO2 binding in it, or whatever else, right? So the enzyme is trying to lower the activation energy, which, as you remember from chemistry, is this part, right? That's the activation energy. The enzyme lowers that from, say, there to this. So this is a lot less energy then that is needed to turn, say, CO2 into bicarb. So the enzyme thinks that, you know what, it'll make the oxygen a lot happier if I have a little plus charge here. So that means that this can easily go and bind and break this bond. And then they can actually have the reaction, stabilizing the transition state that has a weaker bond right here, so the oxygen can easily go and bind. So that's the tie-in with organic. So I know you guys know this is math, and so you know that this bit's been coming up. You actually have an equation. Try to make it as brief and painless as possible. So the rate equals change in product over time, and this is yes, it's calculus. You won't have to do any. Don't worry, you're safe. And that's equal to V max times concentration of substrate over Km, the Michaelis-Menten constant. Oops, I'm going to fix that. Plus concentration of substrate. So you're like, okay, I don't know where that came from. So you can derive it. It's possible to derive it from the initial bits, but that would actually probably take 15 minutes. And I haven't found to be helpful, and most of the people don't find it that helpful. So if you want to find it, I'm sure you can find it somewhere. But instead, I'm going to go through a couple base cases in which show what this equation actually means. So I'm going to plot out now the basic graph of what's happening here. This is rate, and this is concentration of substrate. So the rate starts out at 0 substrate. Obviously nothing's happening right here. It goes up and then it levels off. So the place that it levels off to we call V max. This is the maximum that you can create. I'll talk about it further in the next video, but it's a good way to think about it is you're using up all the enzyme all the time. There's no more space for the enzyme to be used. You hit a maximum rate. You can also convert this, because obviously this equation looks very hard to use. And you know what's much easier? Y equals mx plus b. I mean, you learned that probably back in 6th grade, 7th grade. It seems a lot simpler to use. And so let's make this in that same form. 1 over rate equals Km over V max times 1 over substrate plus 1 over V max. You look at me and you wonder, that didn't make it any easier. It did. Because I'm going to decide that 1 over rate equals y. And 1 over s equals x. Okay. So now we have 1 over rate, which is y equals Km over V max times x plus 1 over V max. So these are all constants, Km and V max. So now you have y equals m slope x plus the intercept, which is 1 over V max. This latter one is called a Lineweaver-Burke plot. After the guys who wanted to make their lives a lot easier. So 1 over rate, 1 over concentration of substrate. And this then forms a nice, pretty, change colors to make it a little bit easier for you guys. It forms a nice, pretty line. We're like, okay, that looks a little bit nicer. It's a pain to deal with in some ways, because I need to take it 1 over something. But okay, it actually makes it a lot easier, because this is how, if on your MCAT, they give you an equation and some numbers, you can determine from this Lineweaver-Burke plot whether an inhibitor is a competitive inhibitor, a non-competitive inhibitor, or an uncompetitive inhibitor. But I'm getting ahead of myself. So next what I'm going to do is I'm going to talk to you about what all this really means, because they won't have you go through this. They won't have you go through this equation ever. They'll give you probably 1 of 3 cases that is very useful for understanding what this equation actually means. So that's what I'll do next in the next video.